Good morning, students. I am Dr.R. Rohini, Assistant Professor of Mathematics, Cardamom Planters Association College, Bodinayakanur. Today topic is sequence. A sequence can be thought of as a list of numbers written in a finite order, A1, A2, A3 and so on, and AN and so on. The number A1 is called the first term, A2 is the second term, and the general term AN. We will deal explicitly with the infinite sequence, and so each term AN will have a successor or AN plus 1 sequence, but we usually write the AN instead of the function notation f of n for the value of the function at the number n notation. The sequence A1, A2 and so on n equal to 1 to infinite denoted by a an. Example, some sequence can be defined by giving a formula for the nth term. In the following example, we give three description of the sequence. One by using the preceding notation, another by using the definition formula, and the third by writing out of the terms of the sequence. Notice n does not have a start at once. Examples sequence. A sequence is such as one examples an equal to n by n plus 1 can be pictured either by plotting in terms on a number line as a figure 1 or plotting its graph in the figure 2. Sequence. Note that since a sequence is a function whose domain is a set of positive integer, its graph consists of isolated points with the coordinates x a, 1, a1, 2, a2, 3, a3 and so on n, an and so on. From figure 1 or figure 2, it appears that the terms of the sequence an equal to n by n plus 1 are approaching 1 as n becomes a large. In fact, the difference 1 minus n by n plus 1 equal to 1 by n plus 1 can be made as small as we like by taking n sufficiently large. Sequence. We indicate this by writing in general notations n tends to infinite limit n by n plus 1 equal to l. N tends to infinite an equal to n means that the term of the sequence an approaches l, n becomes a large. Sequence. A sequence an has the limit l. We write n tends to infinite an equal to l. An tends to l as n tends to infinite. The term an as a close to l we like by taking n sufficiently large. N tends to infinite an exists. The sequence converges, otherwise sequence is a diverges. Sequence. Some examples of the graph. Sequence. A more precise version of a sequence an has a limit l. We write n tends to infinite an equal to l. An tends to infinite as n tends to infinite. Definition. For every epsilon greater than 0, there is a corresponding integer n such that n greater than n, then an minus l is less than epsilon. Some definition of the sequence. The points of the graph an must be lies between the horizontal line y equal to l plus epsilon, y equal to l minus epsilon. The picture must be valid no matter how small epsilon is chosen, but usually a smaller epsilon requires a large. N tends to infinite f of x equal to l, f of n equal to an when n is an integer. N tends to infinite an equal to l. So some definitions, some limits of the law. The theorem can be adapted the sequence as follows. Bn lies between an to an, then n tends to infinite an equal to n tends to infinite cn equal to l, then n tends to infinite bn equal to l. So next, n tends to infinite modulus of an equal to 0, then n tends to infinite an equal to 0, an equal to l, then the function f is continuous at l, then f of an equal to l. Some examples, some solutions, some graphs. The sequence Rn convergent if r lies between minus 1 to 1, divergent for all other values of r. N tends to infinite Rn equal to 0 if r lies between minus 1 to 1, if r equal to 1 equal to 1. A sequence an is called increasing. An is less than an plus 1 for n is greater than or equal to n. So a1 less than a2 is and so on is a decreasing sequence. If an is greater than or equal to an plus 1 for n is greater than or equal to n. A sequence is a monotonic increasing or decreasing. Some bounded definition. An is a bounded above if there is number m. Am is less than or equal to capital M. Bounded below m is less than or equal to an. It is bounded below or above, then an is a bounded sequence. Every bounded sequence is a convergent an equal to minus 1 to n. So an lies between minus 1 to 1. Not every monotonic sequence is a convergent. Sequence some examples. Application of axioms. So sequence. Thank you.